Welcome everyone. Thanks for joining to this first workshop from the Quantum Meetup here in Barcelona. Quantum Computing and Qiskit for Dummies. It's really exciting. In this workshop, the goal of this workshop is basically to introduce Qiskit, which is an open source written in Python computing framework or programming framework. And this workshop will serve as an introduction for the next workshop, which is going to be held next Wednesday, okay? And it will be about quantum machine learning, which is a field inside quantum computing that explores the intersection of artificial intelligence and quantum computing. So this will come very handy, very useful for those who maybe haven't had a formal introduction and want to start on to the path of quantum computing, and maybe join also next week's workshop. So this will help a lot. So the agenda and the topics that will be covered will go from the basics of the quantum computing. We will talk about quantum states, registers of qubits, the notation that it's used, and the quantum gates that are used to perform operations on a quantum circuit. We'll also talk about how to generalize that to multiple qubits, and we'll talk also about the typical phenomena that appears in quantum computing, such as superposition, entanglement, and so on. So bear with us. The workshop is going to be conducted by Carmen Recio, she's a mathematician, and she's also involved in a lot here in Spain in the quantum computing community. She's an IBM Quantum Computing Ambassador and a Qiskit Advocate. So I leave it to Carmen to start the workshop, and thanks everyone for joining. You also will have time to ask questions or during the chat, or maybe you raise your hand and some of the panelists will unmute you to ask questions and interact with us. So, Carmen, I leave it to you.
Okay, thanks a lot, Ricardo, for introducing the workshop, and hello everyone. I'm very happy to be with you this afternoon. So, as Ricardo has said, today we're going to make an introduction to Qiskit, and I hope you will all be ready for next week's event, which is a little bit more advanced. So let's start with the beginning. Okay, so first of all, as you probably saw in the prerequisites, you had to sign up in this link. If anyone hasn't done it, don't worry, it doesn't take too long. So you just follow this link and you will go to a web page, to this web page. I'm going to refresh it. And here, once you have signed up, you can use your email or your LinkedIn account, your Twitter account, anything, a lot of things, or just a personal email. You get access to the IBM Quantum experience, which is really cool because you have some quantum computers in the cloud that you can use. Okay, so these are the backends that we are going to use for the workshop. Okay, let me tell you a little bit about them. You see that in each backend, you have the name of the backend, and then you have the number of qubits that they have, and also something which is QV and a number. This stands for quantum volume. It's a metric that we use in order to measure how good the hardware is progressing. And because in today's hardware, for those of you who don't know that, we are in the NISQ era. NISQ stands for Noise Intermediate Scale Quantum Devices, and that means that we don't have error correction yet. So in the results that we are going to get from our experiments, we are going to see a little bit of noise. Okay. You don't have to worry about that because there are also techniques to mitigate that noise, and we will talk about that later. But so that you know, the greater this quantum volume is, the better the processor. So depending on the experiment you want to do, you might want to look at the number of qubits that you need and choose the highest quantum volume available. Okay, so right now you can scroll down and see all the backends you have access to. They are all based in Poughkeepsie, in New York, in a center, a quantum computing center that we have there. And even if they have names of different cities, that's just in honor of the researchers, but they are all based in New York. Okay, and something that is also very important is that we have a special backend which only has 1 qubit, and this is mostly for hardware experimentation. And another very important thing is, I'm going to try to put this down. Okay, it's the Quasam Simulator. Okay, the Quasam Simulator is not a quantum computer. This is a classical computer. Actually, it is based in some machines that are also used in high-performance computing. That's why we will see later that they are called high-performance simulators. And it can simulate up to 32 qubits. Okay, it doesn't just simulate how qubits should behave in an ideal world, but it simulates real backends from this era. So it also simulates noise, and we're going to see that. And as you might have seen, there are a number of jobs in queue, because this is open access. We have to control somehow how the jobs are scheduled. Okay, and don't worry, it's not usually so busy, but this week, actually, since last week and for a couple of weeks, there's going to be the IBM Quantum Challenge. So now it's very busy because of that, okay? But it's usually not that busy. So for today, we will probably be using the simulator, which is the quickest one, but don't expect to see it always that busy. Okay, so here we have, this is the platform we're going to use for the workshop. So I'm going to make a little tour so that you get familiar with the tool. We have this window, and also it's important that, for instance, when you're going to do some advanced experiment, you also have to take into account what the topology of the qubits are, and also so it's very important to know, in order to choose the qubits we are going to involve in our operations, is very important to know what is the error associated with single qubit gates. These are like the operations that we do in one single qubit, and the CNOT error rate, which has to do with another operation that involves 2 qubits instead of 1. Okay, so here with the colors, we can see what is the error associated to that kind of operation for each qubit. So for instance, if we wanted to do some operation with 2 qubits where we want to minimize the error, we will choose accordingly the ones that have the least, the minimal error in the processor. And we can check the topology of all of them, because sometimes, well, these two are exactly the same, but let me think, this is different. Sometimes it will be interesting for us to know the topology, because maybe we want to do some operation that involves 2 qubits and we want them to be connected. So here we will then involve 0 and 4 for a 2-gate operation, because we will require extra operations in order to get from one qubit to the other. We will just use 2 that are connected. Okay, so this is also important. These computers are calibrated every day. So here you can download the latest calibrations, and you have the date when everything was calibrated again. Okay, so with that, I think we know enough about the backends, about the quantum computers that we are going to use. I think it's quite cool, maybe for those who are new. You started here, you joined here today without a quantum computer. Now you have like 8 or so, and a simulator. So not bad. And now, okay, in this window we have the results of previous jobs that we have sent to the quantum computer. And now, how do we do the experiments? Okay, today we're going to focus. I'm just going to use this part in order to explain concepts in the introduction to quantum computing. But this is a graphical composer, and today we're not going to focus on that. Okay, I'm gonna just use it to illustrate the examples. So here, what we have is this is the composer. Each line that starts with a Q sub something represents a qubit. They are all initiated into the 0 state by default. And then since we have to do something that we call measure, we have to like look at the qubits and write down somewhere what that value is. So for that, we have some classical registers, which are the ones that begin with C from classical. Okay, so if we don't do anything, if we add an extra qubit, you see that automatically another classical register is added, because we usually are going we will want to measure all qubits. Okay, so in order to have somewhere we can store that measurement, we have to add one classical register per qubits. Maybe if you keep learning about this, you will find some cases where there are some qubits that you don't actually measure. So in those cases, maybe we don't need the exact same number of qubits and classical registers. So that's also possible to be edited. Okay, so now I'm going to just stay with one qubit. And here I have all the operations or all the basic gates that I need to build all the operations that I might want to do in quantum computing. So how do I apply an operation to a qubit? I just select the operation that I want, and I put it on top of the qubit line, of the qubit register. Okay, so, and then you have seen that these graphics that are here have changed. I'm not going to explain yet what they are, but they give us an idea of how the state of the qubit is changing. But I still have to explain what is the state of a qubit. Okay, so the idea from this part is that we are going to have a graphical place, a graphical composer, where we can see how operations affect to our qubits. And we are going to have also some graphical representations that will help us understand what is going on. Okay, and the second thing we're going to use, and this is the most important thing for today, is the quantum lab. Okay, the first time it surges, it takes a while, and well, to be honest, sometimes it fails, but you just have to refresh and it's fine. Okay, the idea of this environment is to have an up-to-date environment where you have the latest version of Qiskit installed. Okay, but it's not the only place where you can use Qiskit. Qiskit, as Ricardo has explained, is a quantum framework. Let me go to the main page of Qiskit. And it is written in Python, okay? So it provides us with a framework that enables us to write our quantum programs in a high-level language, so that we don't have to go until the low level of the gates and even lower. the micropulse level. Okay, so it is very easy to learn. Today I'm going to make you a hands-on, but here you have a lot of information, like the documentation about how to get. Okay, this has changed. Every time I do a demo, something has changed. Okay, just the appearance, but okay, so here you have all the documentation. So anything you might want to learn about, you can come here. And also the learning resources are here. So you have the Qiskit textbook, which is very useful in order to learn, and it has coding examples. And also you have in YouTube, I think here, some videos to help you learn how to program with Qiskit. So apart from the tutorial, from the workshop we are doing today, you have these other educational materials to continue learning. Okay, but let's see what is Qiskit, okay? And let's talk about the Qiskit elements. Okay, so we have like the full stack story here. We have the hardware that is in the cloud, and we can access it from the IBM Quantum Experience or by installing Qiskit in our own computer, and then with our account. I will tell you how to do that too. And then we have the framework Qiskit. Qiskit has 4 elements. The first one is Terra, which is kind of the core. It has all the elements that we need in order to build the circuits, the gates, etc. And all the other elements rely on Terra. Then we have Ignis. I mentioned that today's quantum computers have noise. So we have to do something to fight that noise. So with Ignis, we have some techniques and some tools in order to characterize, because first we have to know what does the noise look like, and also to mitigate that noise. Once we have characterized it, let's think about how to mitigate it. Okay, so Ignis provides us with tools for that. Then Aqua. Aqua is a set of libraries of quantum algorithms, basically. Okay, so here we have some classes that implement quantum algorithms, and I hope we can see at least one example, but if not, I think in the workshop next week, you will use it. So for Aqua, you have quantum algorithms, and it's divided like in modules. So there is a module for chemistry, a module for finance, a module for optimization. There used to be one of machine learning, but they have been changing that. I think now they don't put it separately. And well, you have mostly most of the algorithms that are published. Okay, and finally we have Air. Air is the part of the classical simulators of quantum computers. Okay, so here what we do have is some tools in order to execute our experiments in simulators. And why are we doing that? Because at this stage, since the quantum computers are not mature enough yet, we have the classical simulators that enable us to double check if the noisy backends are doing what they are supposed to do. Okay, so they help us to learn about quantum hardware, and also for the scale of the experiments that we're doing today, it's enough to have a simulator. Okay. Not for the ones that we would like to do, but for the ones that we do in the in the workshop. Okay, so well, we will see all the 3 simulators, well, 3 of the 4 simulators that Air has, and you will learn how to use it. Okay, so with that, let's talk a little bit about what is the state of a qubit and some concepts like the Dirac notation. Well, some of you maybe recognize this document because it's from the Qiskit summer school, and we're not going to go through all of it because it's like 2 hours and a half lesson, but you have the full video if you want to keep learning. I'm just going to explain what I need for the workshop today. Okay, so let's start with the concept of a qubit. Okay, what you're used to is the classical computing, and in classical computing, what is the basic unit of information? The bit, and the bit is can only have 2 possible states. It can only be 0 or 1. Well, in quantum computing, there is a new paradigm because at the most basic level, it's already different. The basic unit of information now are qubits, and the qubits can have many more states than just 0 or 1. They can be 0, they can be 1, or they can be what we call a superposition of 0 and 1. Okay, and in order to represent states, we are going to use this notation. Okay, so from here, don't worry about all the text. Just focus in the things that I'm highlighting. Okay, so we have this notation that Dirac, the famous mathematician, created, and when we have this ket, this one is called ket. Okay, when we have these 2 signs, and A is basically a column vector. Okay, so if we see this notation, it means that we have a column vector. Okay, what happens if we see it the other way? The arrow is pointing to the left. Well, in this case, what we have is the complex conjugated transposed. Okay, so what does this mean? If each column becomes a row, and then that's what the transpose does, and then we take the complex conjugated of the elements that appear inside the vector. So since these are complex numbers, what we do is we take the number with the imaginary part with an opposite sign. Okay, so well, you just need to worry really about this notation. Yes.
We had one question that someone wanted to know this lesson of the Qiskit introduction that you show these notes. Are they online available? Can you share the link?
Yes, well, they are not in PDF format, but you have the video of the lecture. So we will share that. I'm going to write it down, and we will share that in the meetup event. Okay, I'm writing it down.
Okay, but I think I wanted to have all these lecture notes that you share here. I mean, the full 2.5 hours.
Yes.
Is that available? Okay.
Yes, the video is available. Not this video. I'm not referring to this video. In the Qiskit YouTube channel, there is the full lesson. Okay, so you can go through all this math if you want it. Okay. Okay, so thank you for that question. Okay, so in the case when we have the state 0, the one that I told you is initialized in the quantum experience, we are really referring to this vector. Okay, it's a column vector, the first one in the canonical basis. Okay, and the one state, we are really referring to this vector. Okay, and any other, well, let me, wait 1 second. Okay, let me change to this document. I'm not going to explain it all. I'm just going to explain that the way we represent a qubit is by using a representation of what we call a 2-dimensional Hilbert space. Okay, a vector space in the end is just a set with two operations that satisfies a series of properties. But right now, I don't want you to worry about this. I just want to tell you that the one we choose for the qubits, it's the one you see here. Since we have a vector space, in vector spaces we have bases. So the bases are the elements that allows us to represent any other element, any other vector in the space vector as a linear combination of the elements in the base. Okay, what does that mean? If we had another state, another vector, since this is a basis, there are two complex numbers because we have defined the Hilbert space is defined in the field of the complex numbers. So there exists, we know that for any other state that the qubit might take, we have a complex linear combination of the elements in the base. That is, there exist two complex numbers, alpha and beta, such that x equals alpha times the first element in the base and plus beta times the second element in the base. Okay, so and there are more bases, of course, but this one is very interesting because it's orthonormal, which means that the elements in the basis are orthogonal and they have norm 1. Okay, so why am I explaining all of this? I'm not trying to bore you. I'm just trying for you to understand how we represent mathematically the state of a qubit. Because these numbers that appear here, the coordinates of this vector corresponding to the basis, are very important. They have a meaning. You remember that they are complex numbers. So complex numbers are equivalent, okay, to points in the plane. So if we draw a point in the plane, there is a distance from the origin to that point in the plane, right? So I'm gonna show it to you here in this example. Okay, if we have the number, for instance, 2 plus 3 times a, we should go 3 times in the x-axis and 2 times in the imaginary axis, and we will have this point. Okay, so how far is it from the origin, from the 0, 0 point? That is called the module of a complex number, and we can use Pythagoras to know that it is the square root of a squared plus b squared. Okay, so if we take the module of alpha, alpha is a number that is, for example, 2 plus 3i, like the one I have explained, is a complex number. And we take the module and we take the square, then that number is the probability of observing 0 when measuring the qubit. And if we do the same with the coordinate that accompanies 1, that is the probability of observing 1 when measuring the qubit. And we know that this is a probability distribution because since we have chosen carefully the vector space and the basis, we can demonstrate that this adds 1. Okay, so with that, we have a probability distribution. And what is measuring? Okay, for that, I'm going to explain a metaphor which is not very accurate scientifically, but I think for the first time you see these quantum bits, the qubits, is very useful. Okay, so we are saying that the qubit can take two values. Okay, it can be 0 or it can be 1. If we while it is in a superposition state, like here, it's a little bit of 0 and a little bit of 1. How much? What alpha and beta will tell us when we take the module and the square. Okay, so imagine that we have, for instance, a coin. If we toss the coin while it's in the air, there is a probability that it's going to be heads, and there is a probability that it's going to be tails, but we don't know what it is. What will we do to know what is the probability associated to face and tails? What we will do is toss the coin, like for instance 100 times, and write down how many times we obtain heads and how many times we obtain tails. Okay, and with that we can estimate the probability. If the coin is fair, we should obtain more or less 50-50. If it's tricked, then maybe we obtain 30-70 or whatever. So with the qubit, it happens the same. While the qubit is in superposition, it's a little bit of 0 and a little bit of 1. And while it's in the quantum, in the superposition, we don't know which one is going to be, and we cannot estimate, we cannot see the probabilities. So what we do? We repeat the experiment many times. We measure every time. Sometimes we will get 0, sometimes we will get 1, and with that we can estimate what alpha and beta were. Okay, so now let's do an example of this. Okay, now that that we know a little bit of the of how a quantum state is represented. Okay, so we are coming back to the circuit composer, and now I have I don't remember how. Okay, delete. You have to click in the, if it's Mac, Control click, and if it's Windows, the right part of the mouse. Okay, so we have a qubit, okay? And now we are going to talk about the probabilities, because we already know that we have to measure it and that this is going to be a probability. So here, see that since I already told you that they are initialized to 0, what we see here is that since the qubit is 0, it's like if we have 1 multiplying the 0 plus 0 multiplying the 1 in the representation that we saw with the Hilbert vector spaces. And now, so now in this graphic, what we have is that if we measure all of the times, we're going to see to observe 0. Okay, the Q sphere, I'm not going to explain it because it's not worth it for this workshop, but you can maybe watch that in the YouTube video. And then, okay, I told you that the modulo of alpha to the square is the probability of observing 0 when measuring the qubit. But what about alpha? What is alpha? Alpha, before we take the module and before we elevate it to the square, we take we make the square. Well, alpha is what we call the probability amplitude. Okay, so sometimes maybe you have heard, okay, in quantum mechanics there exist negative probabilities. That is not true. There is nowhere that there isn't any place where a probability can be negative, but the amplitude of probability can be well, what's more, it can be negative, or it is a complex number in the end, so it can have a real or imaginary part, any of them negative. Okay, so here, what do we have? If you see, these are the coordinates with respect to the basis. So since we know we are in 0, see, the computational basis states are 0 and 1. So here what we have is that we have a 1 multiplying the 0 and a 0 multiplying the 1. And what is this plus 0j? I don't understand why, but the world of Python and in general in computer engineering, they call the imaginary unit j. Okay, I don't understand why they don't call it I, but it's the same. Okay, so here, since the number is real, we only have a real part. So it's 1 multiplying the 0 plus 0 multiplying the 1. So here, if we measured, and the measure is this, it's this operation that you see here, we already know what we are going to observe, because what we are going to observe is the probability. So we know that any number of shots that we establish for this experiment is going to be always 0. All the times that we measure, it will be 0. Okay, when not measuring the same experiment. Okay, an experiment means initializing to 0 and then measuring. The second experiment is initializing to 0 and then measuring. Okay, so this is not very interesting. I'm going to just erase it. I'm going to do another example, which is very often used as the first iteration in many algorithms. And this way I can introduce you to another gate. Following the formal representation, you already might have realized that the quantum states in the end are vectors. So right now, let's think what are the gates? The gates in the end are just matrices. Okay, and if we went here and open the glossary, here you will see more information about what each gate is. Okay, what they do, and well, previously there was also the matrix, but well, you can find that in the internet. Okay, so if you see, for example, the Hadamard gate, which is the one that we are using, they explain us what it does. Okay, so but let's find out this way. So we have one qubit, we have a classical register where we are going to store the measurement, and we have the Hadamard gate. Let's try to figure out on our own, just by looking at these graphics, at these two graphics, what's the outcome of what the outcome of the measurement is going to be. Well, the first graphic talks us about the measurement probabilities, what we see after we measure. And in this case, what it's telling us is that 50% of the times we will observe 0, and 50% of the times we will observe 1. This is what we call uniform superposition. So with this gate, we have created uniform superposition. We have an interesting state that we cannot have in the classical world. And then in the state vector, we have the information about the actual alpha and beta, from which we then take the module and elevate to the square and get these probabilities. So what is this number? I'm going to tell you. It's 1 over the square root of 2. If you do the square of that, the module is the number itself because it's a positive real number, and then the square cancels out with the square root, so we have 1 over 2, which is 0.5, which is 50%. Okay, so now let's run an experiment. We're going to put the measurement operation, and we're going to define the settings of our experiment. So here we have the provider that we have access to, the free one. I also have only access to this one. Here we have, we can set up how many times we're going to repeat this experiment. So let's leave it like this. And here we can select the backend. Okay, so I'm going to go with the simulator because I think it's going to be the one that takes less time. And then we run it. Okay, so it is created here. And you see that it's completed. So we can open it and see what we got. Okay, so in this case, what we get is a histogram with the probabilities, and we see that of these 124 times that we repeated the experiment, 51.76% of the times we observe 0, and the rest of the shots we observe 1. So the probabilities are more or less 50-50. What happened? Why didn't we get exactly the perfect solution of 50-50? It's because as I told you in the beginning, even the simulator is simulating noise. Okay, so now let's see how we will do this same experiment, the experiment that we did here, the Hadamard gate with the measurement. Let's see how we will do it with Qiskit. And this way we can start with our first program in Qiskit. Okay, so you should go to the Quantum Lab and you will see that you have all the tutorials here. Okay, and these are also updated with the version of Qiskit. So you always have the latest tutorials. Okay, so now let's go to circuits, and we will use the tutorial getting started with Qiskit. Okay, so in this case, there are a lot of things that are explained in this tutorial. I'm going to show you how to build the same experiment that we did before, and how we can execute it first in a simulator, in the Quasam Simulator, the same one that we use from the Composer, and then with your credentials in a real one. Although, since there are so many experiments going on right now because of the Qiskit challenge, we will not execute it. You can do that later when the quantum challenge is over. Okay, so, well, as you see, this is a Jupyter notebook, and what we do first is importing the libraries that we are going to need. Well, in this case, they don't think it too much. We just import NumPy, and then we import everything from Qiskit. Okay, and this is just for the things to show directly in the screen. Okay, so the first thing that we are going to do is to create a quantum circuit, but we were acting not in 3 qubits, but in 1. So I'm going to change the number here. Okay, so with this command, I have created a quantum circuit with only 1 qubit. Okay, and now what are we going to do? The only operation that we were applying is adding a Hadamard gate to the qubit in the position 0. Okay, so I have commented the rest of the things because here it was a little bit more advanced, and we are going to just leave this outcome. Okay, so now we have also some tools to visualize what we are doing. Okay, so in this case, I have created a quantum register followed by a Hadamard gate. But there is something missing, because in the other Composer, I also had the measurement and I had the classical register where I was going to store the measurement, right? So for that, since I'm going to want to run an experiment, I'm going to first import the backend that I'm going to use. Okay, it's not this one. Well, but yes, I will explain this too. Before we do the exact same experiment that we had before, since I wanted you to know all the 3 most used backends, let's also import the state vector simulator, but taking into account that this is not exactly the same backend that we used before. It was called Quasam. So this simulator, what do you think it's going to do? It's not rocket science, the name itself says it. So what it's going to do, it's giving us the state vector. Okay. So what we do is first we create a Quantum program for execution, and we tell them what is the circuit it has to act on, and what is the backend that we defined before. And we use this to store the result. Okay, so now let's print the result of our state vector. And the state vector, what was it? It was the coordinates with respect to the base. So this is what we expected: 1 over the square root of 2. If we take the module, in this case it's a real number, so the module is the number itself. sorry, it's the absolute value, but it's a positive real number. So it's the number itself in this case. And then we take the square. So the square root cancels with the square, and we will have 1/2, which is the probability. But here we are not talking about the probabilities, but about the amplitude, the probability amplitudes. So this is exactly what we got in the other case. And now we also have this, the plot state. Okay, I don't know why this is looking so weird. Let me run it again. Okay, yes, because I'm only using 1 qubit. Well, it's fine. Okay, in the end, what we are getting is what is the real part and what is the imaginary part, but there is some kind of problem for only 1 qubit. Okay, but what we are getting here is just a visualization to see what is the real part corresponding to each of the states and what is the imaginary part. The imaginary parts here are 0, so it's 0. Okay, so we also have another simulator, which is also quite useful because in the end, before we measure, okay, let's go back here. All the operations that we have here, I told you that they are matrices, and you're going to have to believe me because in 1 hour and a half, I don't have time to explain more formally everything. But most of the gates are matrices. If they are only for 1 qubit, so 1 qubit is a vector of a 2-dimensional column vector, then the matrices are going to be of dimension 2 times 2. They are square matrices. Then if we have a matrix, a gate, sorry, for more than 2 qubits, if it's for 2 qubits, then the possibilities, we have many more possibilities. We have as the possible basis states are 0, 0, 0, 1, 1, 0, or 1, 1. So all possible combinations of 0 and 1 allowing repetition. Okay, and so these are all the possibilities. It's 4 possibilities. So then,
Carmen,
yes.
Sorry to interrupt you. There was another question asking specifically about this. So what's the difference between the probabilities and the amplitudes? Why do you get 0.7 and 0.5? Was the question.
Okay, let me go back then to here. Okay, so well, we know that when I showed you the linear algebra representation, okay, since this is a basis, 0 and 1, it's a computational basis, we could choose another one, but this is a basis, okay, and it's the first one that you always see. We are in a complex vector space. The field, our scalars here are complex numbers. In some other vector spaces, they can be other field of numbers, but right now we are working with the field of the complex numbers. So alpha and beta are complex numbers. They are numbers of the form something real plus something multiplying the I, the imaginary unit, which satisfies that I to the square equals -1. That's the definition of a complex number. Okay, what you have here. The complex numbers are numbers of the form. Okay, maybe it's confusing that I'm using alpha and beta here too, but okay. Don't look look only at this. It's a number of the form A plus B times I. So in the end, since we can represent the axis of the real numbers and the axis of the imaginary numbers, we say that is isomorphism to R2, to the plane, but you can think it's equivalent. So its complex number has a number in the plane that represents it. Okay, so having that in mind, we are talking about complex numbers. Because of the definition of a basis in a vector space, we know that the that the coordinates corresponding to the basis enables us to represent any other vector in the vector space. In this case, our vectors are quantum states. So the coordinates with respect to the basis are complex numbers, and that's what we call amplitude, probability amplitude, the complex numbers that are the coordinates with respect to the basis. But because of the Born rule that I didn't explain, but the Born rules tell us that the probability to observe 0 equals the module to the square of the coordinate accompanying the first element in the basis, and the probability of measuring the second element in the basis, because of this Born rule, tells us that this is the probability of observing one. Okay, so I haven't really explained why, okay, because for that we will need more time. But you just have to keep in mind that the amplitude are complex numbers, and the probability is a number between 0 and 1. Well, it's a probability distribution, a part of the probability distribution. Okay, what has to be satisfied is this condition for it to be a probability distribution, and this is satisfied because of the selection that we made of the vector space. Okay, so I hope that makes it a little bit more clear. The amplitude is the components of the state vector, and the probabilities are those components taking the module and the square. And this is because of a rule that is called Born rule that we are not going to demonstrate. Okay, but well, this is the meaning of these numbers. Okay, so now let's go back to here. I don't remember what I was explaining. Okay, yes. Now we're going to see the second kind of simulator, and I'm gonna spend a lot of time, but just keep in mind that our quantum states are vectors, and our quantum gates are matrices. And they are not just any kind of matrix, but they are unitary matrices. All of the ones that you can see here are unitary matrices, except for these ones that are here. Okay, these ones that are in gray are not unitary. They are another kind of operation. And what is one property of unitary matrices? That anything we do, we can undo it. Okay, and so if I apply a H gate, there is going to be another combination of gates that undoes what H does. In this case, is H itself. Okay, so you can see it here. If we apply H twice, we get 100 probability 0. So we started in 0 and we finished in 0. So what I'm trying to say with that, well, because of the properties of this kind of matrices, if you make the product of two unitary unitary matrices, then you get another unitary matrix. So the product of unitary matrices is a unitary matrix. So if we apply a lot of gates, like, I don't know, this one, this one, this one, and this one, in the end, what am I really doing? If I were to do it with my pencil and my paper, I would write the 1, 0 vector that represents the first element in the base, the 0, and then I will multiply it by this matrix, then by this one, then by this one, and the result by this one. So what can I do instead? I can multiply first all the matrices and apply it directly to the vector. So we kind of have an equivalent unitary matrix, which is the product of all the unitary matrices that appear in my circuit, that is that represents this circuit, and that is what we wanted to do here. Let me see here. Okay, with this second backend. In this case, since we have imported everything from R, now we also have access with get backend to this second kind of simulator, which is the unitary simulator. I'm going to run it, and in this case, I get the H gate because I have only applied one gate. So this is exactly the Hadamard gate. Okay, let me show you how it looks like. Gate matrix. Okay, so here you have the matrix that represents it. Okay, so in the end it's 1 over the square root of 2 multiplied by 1, 1, 1, and minus 1. And what did we get here? Exactly that. We can put 1 over the square root of 2, which is 0.707, etc. Out of it. Take common factor, it is multiplying this one, this one, this one, and this one with a minus, so it's the same. Okay, so now let's get back to the example that we were doing, because now we're going to add a measurement in Qiskit. Okay, so remember what we had done, let me go back, was just create this. Okay, I had created the quantum register and I had added an H, and it was enough in order to calculate the state vector and to calculate the unitary matrix. But now I want to make an experiment. So I need to add also a classical register. So for that, I'm going to create a measurement, in this case of range 1, and I'm going to create, well, I call it maze because I'm going to measure it, but in the end I'm using the same. I'm using quantum circuit, I'm telling I'm using one quantum register and one classical register. Okay, so I add the measurement, and I use the same circuit that I used before, but I added the measurement and I draw it to see what I have done. Let me see, what did I do? Okay, I added an extra one. And the bar, no, okay, I don't want a barrier, sorry. I'm erasing it. Okay, so in this case, I already have what I wanted: the quantum register, the classical register, and the Hadamard gate and the measurement. Okay, so as you have seen, it's very intuitive, and it's not, the syntax is very intuitive. Okay, so it's actually even, well, not easier maybe than the composer, but it's very easy. So with that, you can build any other circuit that you want with this basic explanation. So here, if you go to the documentation, you go to tutorials circuit. This is the same circuit that we were doing, but here you have a summary of the quantum operations. So here you have an explanation of all the gates that you can do. So an exercise that you can do maybe tomorrow is going through this tutorial and try to build a quantum circuit first with the quantum composer, and then find here how do you do that with Qiskit, and build it with the code. Okay, so this is an exercise. This way you are prepared for next week. When you will see how they build the circuits, you will understand everything. Okay, so now let's get back here. We have built it, but now we want to execute it. So for that, what do? We select as a backend the Quasam Simulator, which was the one that we saw that could simulate up to 32 qubits. And then we create an execution. Okay, we give it the number of shots, the backend that we're using, which is the one we defined here, and QC, which, if you remember, is the circuit plus the measurement. And we store the result here. And from here, we get two kind of things. One of them is counts, which stores what we need is a list in Python and tells us to this first value, the 0, it has been measured 490 times, and the 1 has been measured 534 times. Okay, so now let's use a visualization tool, the histogram, to plot it. And it's the same, more or less, that what we got last time. Due to noise, is not exactly always the same, but we already know about that noise, and it's fine. Okay, so with that, we have finished the first tutorial of getting started with Qiskit. Now, how will we execute it in a real backend? Okay, that's another important question. So in this case, if you are already working in the quantum lab, you don't have to worry about that. But what if we installed it in our local computer? So let me make you an example. Okay, if we install Qiskit in a local computer, which is very easy, you have all the information here. Okay, installing Qiskit in the documentation, and you just follow it. It's available for these operating systems, and you will use Anaconda. Okay, so I'm not gonna show how to install it. You have the video, but for instance, here I have my Qiskit environment, and I'm going to run it in a Jupyter notebook. Okay, so I will just select Jupyter notebook, and it opens here. Okay, so now I have access to all my files, and well, I'm going to show you this one, I think. Okay, no, the one with the solutions. Well, or not, I'm going to just open a tutorial better. For instance, this one, advanced. Okay, I'm going to open this one. Okay, so if I were working here and I wanted to use my credentials, what I will need to do is because this is a Conda environment, okay? I have a Conda environment in my computer that I first created just with Python. I use that environment to install Qiskit, and now I'm accessing the local files that I have in my computer. And okay, so here, how do I tell my Qiskit environment that I have an account in the quantum experience, and that I want to run it from my computer, but I want my experience to be sent to real hardware? Well, in this case, I will have to go to my account, and here I have a token. Okay, so here, this is what I will have to copy. I'm not going to do it, and I will have to use a couple of commands, which is just IBM Q load account, and you put the token with 2 commas, and then you can work, and you can access all the backends that you may need. Okay, also the Quasam Simulator in the cloud, because you can run your experiment in your local machine, but you cannot simulate 32 qubits in your local machine because it will be too much for your computer, probably, unless you have a supercomputer. Literally a supercomputer. Okay, so I thought it was important to show you what it was, but again, in this environment, you don't have to do that because you are already logged in, and it's fine. Okay, but keep in mind that if you are working locally from your Conda environment, you will have to add an extra command where you will have to load your credentials. Okay, so now, Okay, I have 20 minutes left. So I think I'm going to explain a little bit about how Qiskit Aqua works, okay? Because we have seen Qiskit Terra for building the circuits and the visualization tools. We have seen Qiskit Air, the 3 simulators. There is another simulator which is called Pulse, but I don't think it's the topic of this workshop, because that's like for people who want to really understand the hardware. So maybe we will plan another event for that. But for now, you know how to represent a qubit. You know how to execute a simulation. Changing it to a real backend will only be changing the backend and getting some of the real ones. Okay, that the ones that we saw here in the dashboard. Okay, instead of putting backend equals air get backend we will put we will import it from the IBM Q library, and we will select backend equals and the name of the well, the function that makes us that lets us import it, and then the name of the backend. Okay, and another tip: if you ever don't know how to do something, what I always do is going to the documentation. Okay, and here in some tutorial, it's going to appear what you want. Or for instance, imagine that you are wondering, okay, in the experiment that we did, okay, where I am, where was it? Just a second. Okay, I think I lost it. I don't know if the changes are applied, but it's fine. Okay, I'm just going to show you an example of how I find out things. Okay, it changed. Okay, so imagine that, for instance, you don't understand very clearly why here, when we use the simulator, we could get the counts. Okay, or what is this function counts? So in this case, what you can do is if you put it here directly, you will no, not in images. Okay, so you will get you will go here, and in the end it's taking you okay, you could have also thought, okay, what is it? It's a Qiskit, it's something that belongs to Qiskit Terra. So let's go to API references in Qiskit Terra and then navigate. Okay, so here this gives us the information about what the class is. Okay, so counts is a class, it's expecting these parameters. They can give us well, it can give us this information. These are the things that you can do with it. Okay, so here, for anything you have in the tutorials, you have all the information and to understand what it does. Okay, so
sorry,
now
Carmen, to interrupt you, there was another question about when running those simulations, if you can use your GPU or tensor calculation units in your computer to speed up the simulation. Is there any support?
Okay. Okay, I don't know how to do that actually. Because it's do you mean, do you have an integrated GPU in your computer, or is it something external that you connect? Okay, let me see the chat.
I think it was Jose Barranquero. I think he refers to like a dedicated graphics card or special tensor processing units.
Okay. Yeah, no, I know what you mean, but actually the machines in the cloud, they are power systems and they have GPUs. So I think you should be able to do that, but I have never tried it. So yeah, maybe if you can write me in Qiskit in Slack, we can try to figure out how to do that, because it will be an interesting experiment. I don't have the answer right away, but I know that air was being tried in this kind of servers that they had GPUs. So I don't know exactly how it will be done in an external GPU, but what you have to verify is well, for instance, if you are using something like a Jetson, you can install it there. So yeah, in this kind, if are you asking about that, about a Jetson device or something like that? I'm not seeing the question. Maybe we can unmute Jose so that he can reply. Well, if you
Yes.
want, or if not, you can also write in the chat. Okay, I see another question that is if Qiskit can be installed in Visual Studio Code. I think so. I haven't used it from there, but I do think so. Okay. Another question I'm seeing in the meantime is if you run 2 consecutive H gates in the simulator, could you still get some noise, or could you get 100% the zero value? Yes, you will still get noise. Okay. Well, noise is happening because you are doing two operations and you are measuring, which also adds some noise. But since it goes back to zero, I think, well, I think that most of the times you will get 100% zero. I'm not sure about that. Okay, each thing you do adds noise, but when the qubit collapses to zero, I think you will only observe zero, right? Yeah, sometimes when I have done it, I think that's where I saw. I don't know if any of you can reply this question, Fabian, or if you know it quickly. If not,
Sorry, say it again. No.
Yes, they have asked if when you apply twice the H gate, do you get 100% of the time zero, or do you get some noise?
Well, I assume there's always noise, no, on a realistic device.
Yes, there is always noise, but actually I have done that experiment sometimes, and I think, well, we can do it now, but well, Sophia, as an exercise, you can do it because we have only 15 minutes left. But yes, noise is happening, but since it goes back to zero, I think that in the real device, there will be zero. There will be some noise, but very, very, very small. But in the Quasam Simulator, I'm not sure, to be honest. Okay, the different buckets that appears online are real quantum computers or just powerful computers. Okay. The backends that appears online are real quantum computers. The only one that is a simulator is the Quasam Simulator. All of them, IBM Q, Santiago, Athens, Valencia, etc., they are real quantum computers, and you have all the data about their topology and the quantum error, etc. They are accessible via cloud, but they are quantum computers. The Quasam Simulator is a simulator. Okay, I don't see any more Any more questions? Okay, so the one who asked about the NVIDIA GPU or the GPU in general, I know it can be done in Jetson from NVIDIA because it also usually has the Ubuntu operating system, and Qiskit can be installed in Ubuntu. But how to do it? I don't have a tutorial, but it's something that I might wanna do. So maybe for another meetup we can take that as an idea.
There was a comment from Ricardo Garcia that there's support for GPU in Qiskit.
Okay.
And you can install it with the command pip install and then Qiskit -AR -GPU. I will copy this into the general chat.
Okay, thank you.
Thank you, Ricardo.
Thank you, Ricardo. Yes. Maybe you can do the next meetup installing it in a Jetson. No, okay, we will discuss that later. We will find someone to do that because I think it will be a cool demo. So thank you for the questions. Okay, so any other questions so far in the Q&A, or do you see any other questions?
Yes, there was one more question. If there's a simple example of a simple circuit that is faster than its corresponding classical implementation.
Okay, so well, I was going to explain an example of a quantum algorithm using Qiskit Aqua. So maybe I go ahead with that, and let's see if your question gets replied. Okay, because the thing is not that the same circuit. The aim of the quantum algorithms is not that that we will implement the same circuits that we will simulate in a classical computers and they will run faster. No, that's not the objective. The objective here is that we have a complete new way of processing information, and the quantum algorithms take advantage of the of the quantum mechanics laws in order to solve the problems in a very different way. So what gives us a speed up is those algorithms that take advantage of superposition, of entanglement, of interference, and but it's not that we're going to implement the same algorithms that we have in the quantum computer and they will run faster. No, it's new steps to solve the problems, and in these steps we are going to take advantage that we can create superposition, that we can create entanglement, and that's how we are going to get an speed up sometimes. But not any problem will run faster in a quantum computer. So both kinds of computation will coexist, and there are very powerful classical algorithms that run in classical hardware, and we will keep using them. It's for some problems that we cannot solve with classical computers that we have, and for which we have a quantum algorithm where we will get the speed up. Okay, so I have, well, it's 5 minutes. I don't know if it's going to be enough. What learning path? Okay, what learning path would you recommend to someone who wants to enter in the quantum computing? I will recommend you to stay tuned to the events that are organized around Qiskit, because there are some schools like the summer school, also the textbook, and there are also some good online courses like in EDX or Coursera. Well, I'm not sure in Coursera. In EDX, yes, there are some of them, but with all the resources that are free and are online, you can learn about it. So the Qiskit textbook would be a good way to learn, for instance.
There was another question about why alpha and beta, the amplitudes, the probabilities have to be complex numbers. So like, what is the physical reason behind that? Do you know?
Okay. I don't really know how to explain that, to be honest. So yeah, I could recommend you some bibliography where I think you can find that, but I think I will need like more time to introduce the concepts I need to explain that. So yeah, maybe I will share also the bibliography in the meetup event, okay? Vale. Okay, libro.
I think it must have to do something with the Hilbert space, now that it's a two-dimensional complex Hilbert space where these states are part of.
Yes, well, in the Hilbert space is a vector space defined over the field of the complex numbers, but I don't know what's the physical reason, like, because it will have something to do with, well, it will have something to do with quantum mechanics, but I don't know exactly what is the phenomenon that had led to choosing this mathematical representation. But in the book that I will post, there will be this explanation for sure. Okay. Okay, so I don't know if it's worth talking about the last. I'm just going to show it very quickly, and we can do maybe a couple of more questions, and you can review it then on your own, okay? So in the documentation here in the tutorials, for instance, you have the finance module, and here you have some examples about how to use quantum computers for solving a real problem. Okay, so in this case, I will recommend you to look at this tutorial, which solves the problem of pricing a special kind of option, in this case, European call options, but actually in the paper that are cited here, you have a methodology to price any kind of option. Okay, so the tutorial has been done for a concrete kind of option, which is the one whose payoff function is this one, a maximum. And what we're going to estimate is the expected payoff. Okay. Okay, so here you can see how we upload the uncertainty model that represents the initial probability. And well, we first compute it with the parameters that they give us about the options. Then we also have to upload to our quantum circuit the payoff function. So here we draw it. Okay, you can review it because I know I'm explaining this very fast. And in order to estimate the expected payoff, well, since it's a very small example, we were able to calculate before the exact expected value of the payoff function, and now we're going to do the same, but with the quantum algorithm. In this case, the algorithm we're using is the iterative amplitude estimation algorithm, and we give it some parameters that it needs. The first are epsilon and alpha, in order to set the target precision and confidence level for our estimation. And then we are going to give it the state preparation that we had prepared. And well, to understand what the objective qubit is, you're going to have to read it more carefully, and maybe also the paper. And we will run using this class. What it does is it produces some circuits that correspond to loading the probability distribution and the payoff function, and then as many iterations of the algorithm as you define. And then we use this command in order to run an experiment in the Quasam Simulator. We establish the number of shots, and we obtain the result of the estimated value. Okay, in this case, the exact value was 0.1623, and the estimated value that was computed with the quantum algorithm that was implemented with this class, this aqua class, it's very close, as you see, and this is our confidence interval, and we didn't go out from the confidence interval. So it's fine. And okay, so this is a very quick example of how this is done. If you want to explore what this class does, I would recommend you to read the paper and then also check the class in order to understand how this is done. But what it really does is in the paper they explain you how they come up with the circuits and how they come up with the equivalence between the estimated expected value of the payoff and with the output of these circuits that are produced by this class. Okay, but as you see, we don't have to worry about these circuits. The aqua class does everything. We just have to prepare the input that this class is expecting, and then we'll have to think ourselves about what are the circuits that should be equivalent to an iteration or two iterations or whatever number of iterations we want to do of this algorithm. And in this case, I think this algorithm gives us a quadratic speedup against comparing it to Monte Carlo simulation methods. Okay, so this is just an example, and with this I'm going to finish. Let's see if there is another. Okay. Okay, so Ricardo can explain the thing about the GPU. 1 second. I'm going to unmute him. Okay, Ricardo, you can go.
Yeah, I was trying to answer the question of the complex amplitudes. I can give maybe a metaphoric explanation or something similar that might help understand the intuition behind that. And it's that if you think as every quantum state has associated a wave function, or it could be interplay, but if you think as qubit as waves have magnitude and phase, maybe that helps you understand what this. At the end, we use complex numbers in quantum mechanics as a mathematical tool to explain what is going on, to predict the results that happen when you do measurements on these quantum computers or quantum circuits. And it's fundamental that this complex amplitude, these amplitudes are complex, because in many algorithms, this is maybe not so formal, but in many algorithms, what the process to build these algorithms is to first put all your solutions on a superposition, so maybe with the Hadamard gates, and then interfere that solution so that when you measure, you get it most of the times. And this is very not formally explained, but what I mean is that they need to be complex numbers so for interference to happen. So it's essential that they are complex. So if we want to have interference patterns, just like what happens with waves, when you add waves that are not in phase, they cancel out. So these kind of patterns arise in quantum circuits, and that's why we need complex numbers to interpret and understand quantum operations. So I mean, that's maybe my point of view. And
maybe I can also quickly comment. I did some research, and I think the complex wave function, the origin of the complex wave function is the Schrödinger equation, because any solutions of the Schrödinger equation are already complex wave functions or superpositions of those.
Exactly.
Okay, so thanks a lot, Fabian and Ricardo, for the answer. We have written down what we have to share in the comments, and since we are out of time, I just want to thank you all, the panelists, the organizer, Ricardo. And thanks to all the attendees. And we hope to see you next week in the Quantum Machine Learning workshop. You are ready now, so you are good to go.
Thank you very much, Carmen.
Okay, bye-bye.
And see you
Thanks
next
everyone.
week.
Yeah, thank you, Carmen. Bye.
Bye.
Thanks.